see you. So after considering the concept of inductance and considering RL, RLC electric circuits, we are ready to proceed further with the introduction to alternating current topic. And today, that's our plan. We will introduce alternating current. We will consider two cases when we have an alternating current power source connected to an active resistor and to an inductor. So we will see what the difference between them and introduce some key parameters and terms which are necessary to describe AC electric circuits. So, what is alternating current? Who will tell me? Yeah, sure, but a bit more explicitly.
Current that change its direction with a certain frequency.
So magnitude and direction with certain frequency. Okay, so that means that during half of period we have positive direction for current, and during another half of period we have negative direction of current. And actually the same will be for voltage. It will be either like positive polarity or negative during half, like respective half of the period. So usually we operate with frequency, which in European countries and also here in Kazakhstan, what is the frequency of alternating current in our power outlets? That's about voltage. I'm asking about frequency. 630. 630. So there's just one number. Of course, it's measured in hertz. The units are hertz, but it's either 60, what you already mentioned, or another option. It's 50 hertz. So here in Kazakhstan and also all across European continent, we have 50 hertz. In the United States, in Japan, we have 60 hertz. So why it is important? Why we have all our power distribution and all electric grid system operating at alternating current model, not DC model. So what is the key requirement for making this huge distributed and complex system of power network to operate easier if we use alternating current with respect to DC current?
We prevent huge loss of energy during the transmission.
So during transmission, we need to increase voltage in order to save energy, because we reduce current, and current makes a dominant contribution to energy losses during transmission. In order to do that, we cannot generate such. So several times we need to step up and step down voltage with the help of transformers. And if we deal with AC current, that is really easy in comparison to DC case to transform voltage to increase and decrease it by using regular transformer. With DC, there are local power systems which are operating at DC current. However, there you need to use inverters to change the DC to high frequency AC. Then you use transformers, but special transformers for high frequency, and there you can make them much smaller. If the higher frequency, the smaller size of the transformers can be used. And in this case, it can also be operated. However, still it's more advanced and technological system which requires more higher uh, technological maintenance. So that's why the system is organized in form of AC current. So now let us consider that we have uh, an AC voltage source. So we have some power supply which provides AC voltage to an active resistor. So this is this AC power supply connected to the active resistor. So this is resistor R. Here the instantaneous voltage at the terminals of this power supply will be given as delta V maximum times sinus omega t. Omega is angular frequency. And here will be some voltage drop delta VR over active resistor. So now if we apply second Kirchhoff's law to this electric circuit, we can write that delta V minus I times like through resistor times resistance of this active resistor, and that should be equal to 0. So the sum of all potential differences over a closed electric circuit should be equal to 0. So in this case, we are operating with instantaneous values for voltage and current. So that's why we have this small I, which highlights that this is an instantaneous current in given moment of time. So how we define now the instantaneous current? That will be instantaneous voltage difference divided by active resistance. Or in other words, if we apply this time dependence function for instantaneous voltage, we will get delta V maximum divided by R times sinus omega t. So we can represent it as I maximum times sinus omega t, where I maximum will be dV maximum over R. So now once we have the current expressed from the time dependence voltage provided by this power supply, AC power supply, and resistance of the circuit, we can determine potential difference like voltage drop over the resistor. So that will be instantaneous current times active resistance. And that will be I maximum times R times sinus omega t. So now we see that the voltage over resistor and the current through this resistor, they are in phase. So there is no phase shift between these two guys. They are described by the same time-dependent functions. So now let me share the screen with you. Here, this one. So we can introduce so-called phasor vector, which represents which can represent the time dependence of current and voltage. So this is how they look when we have a plot of instantaneous current and voltage drop over resistor as a function of time. It's some sinusoidal function, so we have voltage change over active resistor and current change. As you see, they are in phase, so they reach like zero in the same time, maximum values also in the same moment of time. So how we show it with a phasor is quite convenient for alternating current circuits. We introduce vectors with magnitudes which are equal to maximum values of considered quantity, is either current or voltage. Then we consider that this phasor vector is rotating counterclockwise with angular frequency of, and which is the frequency of the AC power supply. And at each moment of time, the projection of this vector, phasor vector, on vertical axis, which corresponds here for current and voltage, will give us the instantaneous magnitude of this parameter. So here, the length of the phasor vector is maximum value, projection on axis y gives us the instantaneous value. So here we see that these phasors are aligned in the same direction. They rotate counterclockwise with the same angular velocity, means they will move like this synchronically in the same direction over time. And there is no phase shift between current and voltage over like current through the active resistor and voltage drop over resistor. When we apply AC power supply to this active resistor, they will change without any phase shift. So let us come back to our whiteboard. And now we need to introduce important parameter, which is so-called RMS, root mean square current. And why we need to operate with this? Because if we consider average current, so what will be average current for AC case? Over one period, let's say. Average current over one period. We have half of the period positive current and another half the same magnitude but negative current. So if we get average, we get zero. So that doesn't make sense. So that's why we need to operate with power which is delivered by this current to electric circuit. In this particular case, when we deal with active resistor, we want to deal with the electric power dissipated in form of heat over active resistor. And in this case, it will not depend on the direction of current, it depends only on its magnitude. And the reason for that, what is the reason for that? From mathematical point of view, from physical makes sense, because it doesn't matter where current flows, it causes heat dissipation. So in any way, heat will dissipate. But we have one equation which actually tells us clearly that dissipated power will not depend on the direction of electric current. What is equation for the Joule length heat dissipated over resistor when there is some current flow through it? I squared times R. So current I is in second power, doesn't mean if it's positive or negative, it will contribute equally to the dissipated power. So what we need to know now we need to determine at which equivalent DC current we will have the same dissipation of electric energy over active resistor as it happens with AC current with some maximum value Imax. So we want to know how we can substitute AC current with some equivalent DC current in order to dissipate the same amount of electric power at this resistor. Why it's useful? Because then we can operate with this equivalent current, which is called IRMS current, and use the same equations which we previously derived for DC electric circuits. So, because in this case, the amount of heat or power delivered to this active resistor will be equivalent to the AC current. So that's why this is important to be considered. And in order to show this, let us consider this example. So as I said, P average, the average power delivered to the resistor when some AC current is flowing, this will be IRMS square times R. So how we get RMS values? It is square root of some I average in second power. So that is like general approach. But here we will show step by step how we get to it. And then we can show from here that IRMS will be equal to square root of P average divided by R. So from this equation, we see that in order to determine this magnitude of IRMS, we need to determine only P average, average power delivered by AC current to this resistor, because magnitude of resistor we know R. So now let us see how we get it. P average over one period, so it will be 1 over period T of the AC current, will be integral from 0 to time, which corresponds to period T. And here will be I maximum square times R times sinus square omega T dt. So we have instantaneous, like this and this bar, that is instantaneous current which flows through the resistor in second power, and then multiplied by resistor. So this expression here under integral, that is instantaneous power which is dissipated over resistor in our AC electric circuit. To get average, we integrate from 0 to t and divide by period of this AC current. So what do we get? We can factor out several parameters. I maximum square times R divided by t, and integral from 0 to t, and here will be sinus square omega t dt. So we can apply some trigonometric transformation. So we will get I maximum square times R over period t times integral from 0 to t. And this sinus second power omega t we can represent as 1 minus cosinus 2 omega t divided by 2 and dt. So now we deal with two integrals. So it will be I maximum second power times r divided by 2t. And here we have integral from 0 to t dt minus integral from 0 to t cosine 2 omega t dt. So that is equal to I maximum second power times r over 2t. So for this integral we get just t, and for the second integral we get sinus 2 omega t over 2 omega from 0 to t. So now let us see what will be this term equal to. Any suggestions? So what is t period? How we can express t period in terms of omega? Okay, so t is equal to 2 pi divided by omega. So that is the expression. And now looking at this, what will be the equal this term when we apply first instead of t, like instead of time, we apply this period here and take into account that it is 2 pi over omega. So exactly, so we have fraction of pi, and like that will, so it's either pi or 2 pi or whatever, it will result in 0, and then we apply this 0 instead of time, it will be also 0. So no matter what we are doing, this will be equal to 0. So in this case, will be equal to I maximum square times R over 2t times t. So we can cancel out this, guys. And eventually we get that average power dissipated over the active resistor will be I maximum square times R divided by 2. So from here, we can get the expression for IRMS. As you remember, it was square root divided, square root of P, no, it's not average, P average divided by R. That will be equal to square root of I maximum second power times R divided by 2 times R. R and R we cancel out. That will be equal to I maximum divided by square root of 2. So, or we can also write similar for VRMS for voltage, and that will be V maximum divided by square of 2. So that's the way how we determine RMS value of AC current and voltage. And then when we deal with these parameters, we can operate with equations which originally derived for DC electric circuits. So we just determine average power, which is dissipated over active resistor, and then we can calculate the RMS values of current and voltage. So now let us consider another example, which is inductor in AC electric circuit. So we have an inductor L in attached to some AC power source. Again, here is delta V at terminals of the power source, and that is delta V maximum times sinus omega t. And here we have some delta VL, voltage drop over the inductor. So according to second Kirchhoff's law, we can write that delta V will be equal, maybe not, minus L times d I L over dt equals to 0. So we remember from previous discussion that the voltage drop over inductor is defined by the inductance times rate over time of changing the current with time. So it's a first derivative of current over time. So now we know that the voltage delta V can be expressed as L times first derivative of current over time, and that should be equal to this expression. So it's delta V maximum times sinus omega t. From here, we can solve it for current. d I L is equal to dV maximum over L times sinus omega t. So now in order to get the expression for, omega t dt, dt. So now in order to get the expression for the current, we need to integrate this expression over time. So IL is equal to delta V maximum over L integral of sinus omega t dt. That will be minus delta V maximum omega L times cosinus omega t. So we don't deal here with constants because it depends on the initial conditions, and it's not important here. We just need to show the general expression for current. So now we can apply a trigonometric transformation, which tells us that cosine omega t can be represented as minus sinus omega t minus pi over 2. and substitute it here. So eventually we get that current through the inductor will be equal, so minus and minus will cancel out, delta V maximum over omega L times sinus omega T minus pi over 2. So now we see that the voltage and current through the inductor are not in the same phase because we have this minus pi over 2. So the current will always will be lagging behind voltage by 90 degrees, or pi over 2. So we can show it here on this slide. So that's now how it looks. We see clearly that there is a phase shift between time-dependent voltage and current through the inductor. So maximum now are shifted. So we get maximum current when voltage is minimum, and so on. And in terms of phasors, nicely you can see the phase shift between them. So this is the phasor for voltage, and this is the phasor for current. So there is 90 degrees between them. And as you see, voltage is first, current is second. They are rotating counterclockwise. So there is pi over 2 phase shift between them, and current is lagging behind voltage. And both of these like phasors, they are rotating with the same frequency, obviously. So let us come back to this whiteboard. So the maximum current, I maximum, is equal to delta V maximum over omega L. So if you compare it to maximum current with active resistor, let's write it here. I maximum was equal to delta V maximum over active resistance R. So in the case of an active resistor, no matter if it's DC or AC electric circuit, we have the meaning of resistance as opposition to electric charges flow in the circuit. So the larger resistance, the more difficult for these charges to flow. So we see here that in the numerator of these equations, like two equations, we have voltage. So this is measured in ohms, means that this should be also the units for this denominator here should be in ohms. So in order to specify this, that it's not active resistance, nevertheless, it behaves like a resistance. So units are ohms. We call them as inductive reactance. So that is equivalent to active resistance, it's opposition for charge flow in the circuit, but that is opposition of inductor of electric circuit for charge flow in this circuit when we have AC current flowing. Obviously, we do not have any issues with this when we have DC because there is no change of electric current. But when we have AC current, then inductor becomes equivalent as we discussed earlier, equivalent to resistance, and it opposes the change of electric current. And since AC electric current is all about change of current because it changes continuously, then it behaves like some reactive inductive reactance, which opposes this flux of AC current in electric circuit. So we can denote it as XL, that is equal to omega L, and we can represent that I maximum in this case will be equal to delta V maximum over XL, inductive reactance. So as you see, inductive reactance is a function of frequency, while active resistance is frequency independent. So now, any suggestions why inductive reactance, the opposition of inductor to AC current, uh, increases with frequency? Because higher frequency means that current changes faster. If current changes faster, it will result in larger uh, induced electromotive force, or we can call it self-induced electromotive force, which opposes the changes. So it will be in opposite polarity to the driving power supply. So the larger negative electromotive force, the more difficult for AC current will be to flow through this electric circuit. That's why the inductive reactance will increase with increase of frequency. So let us summarize our discussion for today. We started the new topic, which is alternating current circuits. And first of all, we introduced a circuit with AC power supply connected to active resistor. We show that voltage drop over the instantaneous parameters we are talking about when we deal with AC current. So instantaneous voltage drop over active resistor is in the same phase as current which flows through this active resistor, and we introduce such new terms as phasors. So phasors, they help us visualize the current phase shift between current and voltage. Their projection on axis y gives us instantaneous values, and the magnitudes of phasors is defined by the maximum values of current and voltage over some elements of AC electric circuit. So the most important conclusion, we do not have any phase shift between current and voltage for active resistor. We introduced another important parameter, which is IRMS, which is some equivalent DC current, which delivers the same amount of electric power to active resistor as the given AC current. In order to calculate it, we considered average power over one period of AC current delivered to a active resistor R, and then we calculated IRMS as square root of average power divided by R. So that is also valid for VRMS value when we deal with voltage. So it's I maximum of AC current divided by square root of 2. So then we considered AC electric circuit with inductor, have shown that the current always lags behind voltage in inductor. Again, we're talking about instantaneous magnitudes. And when we look at phasors, we do see that first we see the uh, voltage phasor, and then behind it, like lower, we see at lagging by pi over 2 phasor corresponding for electric current. Um, since the opposition for AC current in such electric circuit which has inductor is represented by reactive resistance. So we introduce this parameter. We see that this is frequency dependent parameter. Its units are the same, like ohms, as units for active resistor. And the physical reason why inductive reactance increases with frequency lays in the Faraday's law, and it tells us that high frequency corresponds to faster rate of changing of electric current and means larger negative induced electromotive force, which opposes the AC current to flow through the circuit. So that's why reactive inductance behaves in this way with frequency. So we will continue considering AC electric circuits next lecture, which will be on Wednesday. Thank you for attention and see you next time.